there are three main acid-base theories, and we're going to do them in chronological order. The first one is known as the Arrhenius definition. It states that an acid donates a hydrogen ion in water, an H plus ion, whereas a base donates a hydroxide ion in water, an OH minus. Here's a video of me writing out some equations using the Arrhenius definition. The first one I'll write is an acid definition, or reaction, I should say. For example, something like HCl will dissociate in water to form H plus and Cl minus. This would be an Arrhenius acid due to the fact that it produces an H plus. With the base, Arrhenius pretty much said you had to have something like OH in the compound already, so that you would form the OH ion when it dissolved. So a very limited definition, and the main base that we have to ask ourselves about is NH3. And so again, I'm writing here, you had to already have either the H plus or the OH minus. So what about NH3? It doesn't have either. How do we explain that? That leads us to our second theory, and the more commonly used theory, that is Bronsted-Lowry definition. The Bronsted-Lowry definition states that an acid donates a proton in water, whereas a base accepts a proton in water. So notice here, you don't have to have hydroxide anymore. You do still have hydrogen, but now we call it a proton. And a proton, in this case, is just a hydrogen atom with no electrons. So one proton, no electrons. This theory is better because it explains ammonia as a base, and this is the one we will use for this class. And I have a video of how those reactions would look. Okay, so here we have the Bronsted-Lowry base. Okay, for an acid in this situation, you are actually going to write the water in the equation. And so it reacts with water to form H3O plus. The H from the HCl, which is an acid, donates its H to the H2O, so that you're now producing H3O plus and Cl minus. So this is definition of acid. Acid should be under HCl. I'm sorry if that's confusing. Here is how we explain NH3. NH3 is a base. So H2O acts like an acid now and gives one of its H's to NH3. Remember, it's an H plus, so your product becomes NH4 plus and OH minus. And we'll talk about why I drew a double arrow there and I only drew a single arrow in the first one in a little bit. So notice this includes ammonia as a base. So this is a more complete definition. Again, I'm writing here, this is the definition we will use for the class. You need to know what Arrhenius stands for, but it's more of a multiple choice aspect, not a working out problem. Okay, moving on. The Lewis definition. This is a more current one as well, but it isn't as useful in our type of chemistry. This is something you'll see more in organic chemistry when we really focus on the electron. The Lewis definition states that an acid accepts an electron pair, whereas the base donates an electron pair. So we're not dealing with protons anymore. We're actually dealing with electrons that are being given up and accepted to break the bonds within a molecule. Okay, This explains all traditional acids and bases and a host of coordination compounds, and is used widely in organic chemistry. Uses what are called coordinate covalent bonds, and we'll talk about those when we get back. The reason why we don't use this as much in this class is because for our purposes in equilibrium, we're not going to deal with coordination compounds. So we need to know this definition, and you will use it in organic chemistry, but you won't see it really being applied